So there are two ways of doing number one. I'll do the longer way first, and then I will do the shorter way in the video. So the longer way is that I see that this is a 5-sided shape. So it is a pentagon, and it tells us that in the question. Now we know that in a pentagon, the sum of all the interior angles can be found using the formula n minus 2 times 180. Since the pentagon is five-sided, n is 5, 5 minus 2 is 3, so 3 times 180 gives us the sum of the interior angles of this pentagon, and that is 540 degrees. So I know that altogether, 1, 2, 3, 4, 5 angles in here need to make 180 degrees. I already have one of the interior angles. I know that it is 140 degrees, so now I just need to find the other ones. This 60-degree angle is supplementary with the one next to it, so 180 minus 60 is 120. Let me put that in. Okay. 84 is supplementary with the interior angle next to it. 100 minus 84 is 96. Okay, moving along, the 68-degree angle is supplementary with the angle right next to it. So 180 minus 68 is 112. So finally, the last of the angles would be whatever is left over to make 540 degrees. So let me add up the angle measurements we have so far. 112 plus 96 plus 120 plus 140. And I got 468. So let me subtract 468 from 540. And I get that the last interior angle should be 72 degrees. So the angle next to it is supplementary. So 180 minus 72 degrees is 108 degrees. So the measure of angle X is 108 degrees. So that's the longer way. Now I'm going to do the shorter way. So I'm just going to erase so I can go back to the beginning. So we have the exterior angles mainly, since we only have one interior angle. We have 1, 2, 3 exterior angles. So this time I'm going to find the exterior angles. So the 140-degree angle is supplementary with the angle next to it. So the angle next to it, the exterior angle is 40 degrees. So now we have 4 exterior angles of this pentagon, and we know that the exterior angles of any shape always add to 360 degrees. So I'm going to add the ones we have so far, 40 plus 60 plus 84 plus 68. And I got 252. So I'm going to subtract 252 from 360. And I get 108 degrees for my last exterior angle, which is what I am looking for. The next question is asking us to find the exterior angle DEF of this pentagon. So I know that in a pentagon, all the angles can be found using the formula n minus 2 times 180 degrees. And since it's a pentagon, n is 5, so that's 3 times 180 degrees, which is 540. So all of the angles together, all of the interior angles added together make 540 degrees. Now they tell us that this is a regular pentagon. That means all the sides and all the angles are congruent to each other. Since all 5 of the angles have the same measure in a regular pentagon, I can divide by 5, since there are 5 angles, to figure out what each angle is. So 540 divided by 5 is 108 degrees. So each of these interior angles is 108 degrees. Now I'm just going to fill in, since I don't have a lot of space, the interior angle that's right next to the angle that we're looking for. The interior angle is supplementary to the exterior angle right next to it. So if I do 180 minus 108, I will get the exterior angle, which is 72 degrees. Okay, here I have isosceles triangle RST. That means that two sides are equal. And it tells us in the question that the two equal sides are RS and RT. They tell us M and N are midpoints of RS and RT. So I can conclude that MN is the midsegment of this triangle. Keep in mind, midsegments are half the length of the third side of the triangle, and midsegments are also parallel to the third side of the triangle. They tell us that MN is 3.5 and the perimeter of triangle RST is 25. We need to find the length of NT. So since I know MN is the midsegment of the triangle, I know it's half the length of the side it's not touching. So if this is 3.5, 3.5 times 2 is 7. So I know that this side of the triangle is 7. And since the perimeter of the whole triangle is 25, 25 minus the side that we already have, the 7, is 18. And since these two sides of the triangle are equal, let me divide that 18 by 2, and I get that each side of the triangle needs to be 9. Now, I do know that M and N are midpoints of the sides that they're on, and midpoints do split the sides of the triangle equally in half. So 9 divided by 2 is 4.5, so I know that each half is 4.5. And now I have all the measurements of this trapezoid at the bottom that I need to find the perimeter of. Oh, sorry, we just needed to find NT. I misread that. So we have NT. It is 4.5. Moving along, quadrilateral ABCD. Let me draw a picture so we can clearly see what's going on here. A, B, C, D. Has diagonals AC and BD. Which information is not sufficient to prove it's a parallelogram? AC and BD bisect each other. Well, if the diagonals bisect each other, that does make it a parallelogram. That is a property of parallelograms. So that's not the answer we're looking for. AB is congruent to CD, and BC is congruent to AD. Well, that does make it a parallelogram. If both pairs of opposite sides are congruent, then we do have a parallelogram that is one of its properties. So that's not the answer choice that we're looking for. That does work. AB is congruent to CD, and AB is parallel to CD. Well, if one pair of opposite sides is both congruent and parallel, that does prove it's a parallelogram. That is one of our ways of proving that we have a parallelogram. So this is not the answer choice that we are looking for either. That brings us to our last answer choice, AB congruent to CD and BC parallel to AD. We have one pair of opposite sides congruent and a different pair of opposite sides parallel. That's not the way of proving that we have a parallelogram. We would have to have one pair of opposite sides that is both congruent and parallel. So this is the answer choice that we are looking for. Moving along to number 5. We are told that A is the midpoint of UV, so UV is being split in half. B is the midpoint of UW, so same thing with UW, it's being split in half. And C is the midpoint of VW. So I know that VW is also being split in half. We're given that VW is 7x minus 3 and AB is 3x plus 1. And we need to find the length of VC, of this half of this whole line segment. Well, since A and B are midpoints of the sides that they're on, AB is a midsegment of triangle VUW. And I know that a midsegment is half the length of the side it's not touching, which would be VW. So 3x plus 1, if I double it, if I double the midsegment, I get the third side of the triangle, since the third side is half the length of the midsegment. Distributing inside the parentheses, I have 6x plus 2 is equal to 7x minus 3. Now subtracting 2 from both sides, subtracting 7x from both sides, I have negative x is equal to negative 5. Dividing each side by negative 1, I have x is equal to 5. We need to find the length of VC. So first I need to find the whole thing VW, which is 7x minus 3. 7 times 5 minus 3 is 32. And if this whole thing, VW, is 32, VC would be half, since C is the midpoint of VW. 32 divided by 2 is 16. So VC is 16. That is the answer that we are looking for. In question number 6, we have a rectangle, and we're told that the diagonals intersect at E. Let's think about what we know about rectangles. We know that they're parallelograms, and we know that they have 90-degree angles. We also know they have congruent diagonals. In the question, it tells us that AE is x plus 2. BD, that is this whole diagonal here, is 4x minus 16. And we need to find the length of the whole diagonal AC. AE is half of the whole diagonal. And we know that the whole diagonals are congruent to each other. This is a rectangle. Since a property of parallelograms that also apply to rectangles is that diagonals bisect each other, I know that each half of the diagonals should be the same as each other. So if I double the x plus 2 segment, that will give me the whole diagonal AC. And I know that the whole diagonal AC should be congruent to the other diagonal BD, which is represented as 4x minus 16. Let me solve the equation real quick. Distributing. 2x plus 4 is equal to 4x minus 16. Subtracting 2x from both sides, adding 16 to both sides, I have 20 is equal to 2x. Dividing both sides by 2, x is equal to 10. Now that I found my x value, I need to plug in to find the length of AC. AE is x plus 2. X plus 2 would be 12. Doubling that to get the whole diagonal, it is 24. So the length of each diagonal should be 24. Okay, here we have a rhombus. So before I even get started, let me think about what I know about rhombuses. I know that rhombuses are parallelograms. I know that they're equilateral. I know they have perpendicular diagonals. And I know that the diagonals bisect the angles. So they're also telling me that AC is 18. So this whole diagonal is 18. And we know that BD, this whole diagonal, is 24. Since rhombuses have all of the properties of parallelograms, I know that the diagonals bisect each other. So if I know that the whole diagonal AC is 18, I know that each half should be 9. And if the whole diagonal BD is 24, I know that each half should be 12. So I'm just going to mark the diagram with those measurements, and I think that might be less confusing to look at as well. So each half of AC is 9. Each half of BD is 12. And our goal is to find the length of one side of the rhombus, so any side, because it's equilateral. So I'll just find the length of this side. I pick the side, doesn't matter which side you pick. And I notice that this side is part of this triangle over here. And one of my properties of a rhombus is that when the diagonals meet, they intersect to form right angles. Remember, the diagonals are perpendicular to each other in a rhombus. So now I know that this triangle is a right triangle, as are all these triangles here. And we have a right triangle, and I know two of the sides of that right triangle. One side's 9, and that's a leg. The other side is 12, that's a leg. I need to find the hypotenuse, the side across from the 90-degree angle. So I can use the Pythagorean theorem to find the missing side of the right triangle. For A and B, I need to plug in the legs. It doesn't matter the order. So I'll plug in 9 for one leg and 12 for the other leg. And then I'm looking for the hypotenuse, so I'm going to leave that as the variable. I have 81 plus 144 is equal to c squared. Now, I'm just going to add 144 and 81, and I get 225. Taking the square root of both sides to get c by itself, I get c is equal to 15. It does work out to a whole number. So I find that the length of one of the sides is 15, and since it is a rhombus, that means all the other sides are also 15. Remember that since the diagonals are perpendicular in a rhombus, it does form right triangles. Okay, here we're given a quadrilateral, and we are told that quadrilateral MNPQ is formed by joining the midpoints of AB, BC, CD, and AD respectively. So I need to find this new quadrilateral MNPQ, and the way that I find it is by taking the midpoints of each of the sides. So my first step is to take the midpoint of side AB, BC, CD, and AD. So I'm going to use midpoint formula to do that. Let me find the midpoint of AB first. So that would be -7 plus -3/2, 4 plus 6/2. That is -10/2, 10/2, and that simplifies to -5/5. Okay, so that is point M. I'm going to mark that in my diagram. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right over here. That's point M. Okay, now I'm going to find the midpoint of BC. So the midpoint of BC, that's -3 plus 3/2, 6 plus 0/2. -3 plus 3 is 0. 6/2 is 3. So that is point N. Let me plot it. There we go. Now I need to find point P, so I need to find the midpoint of CD. So to find the midpoint of CD, I am going to do 3 plus 1/2, 0 plus -8/2. So that is 4/2 is 2. -8/2 is -4. So that is point P. 1, 2, -1, -2, -3, -4. So that's P. Finally, we just have to find point Q. So that's the midpoint of AD. And that would be -7 plus 1/2, 4 plus -8/2. -7 plus 1 is 6/2 is -3. 4 plus -8 is -4/2, which is -2. So that's point Q, -1, -2, -3, -1, -2. So now we found the quadrilateral that we were looking for, MNPQ. That's the first part of the question to locate. Let me do that a little bit better. To locate this quadrilateral. Now that we've located it, we need to prove that it is a parallelogram. I'm just going to write some of these calculations so I have more space. I am going to just rewrite the midpoints at the top, but I am going to erase the rest of the calculation. Okay, so the next part of the question is to prove that this quadrilateral is a parallelogram. So all you have to do is pick one method of proving it's a parallelogram and show that it's true. I'm just going to show that the diagonals bisect each other because that's just two more midpoint formulas. So I'm going to find the midpoint of diagonal MP. So I'm going to be using points M and P. So that's -5 plus 2 over 2, 5 plus -4 over 2. -5 plus 2 is -3, so that's -3 over 2. 5 plus -4 is 1, so that's 1/2. Now, I'm going to find the midpoint of the other diagonal. That would be NQ, so the midpoint of NQ. And that's 0 plus -3 over 2, 3 plus -2 over 2. So once again, I have -3 over 2, 1/2. So I see that the midpoints are the same. So I'm going to write here, since the midpoints of the diagonals are the same, the diagonals bisect each other, making the quadrilateral a parallelogram. You do need to end any coordinate geometry proof with a concluding statement explaining how you know what you proved is true. I know this is a parallelogram because I just proved that the diagonals bisect each other by showing that they meet in the same spot. Okay, next question. So the first part of the question is asking us to find SR. So SR is one of the sides of the rhombus. And I know that in a rhombus, one of the properties is that the sides are all the same length. So I know that SR and ST are equal to each other. So I can make the equation 8x minus 5 is equal to 3x plus 30. Subtract 3x plus both sides, I have 5x is equal to, and adding 5 to both sides, 35. Now if I do 35 divided by 5, I have that x is equal to 7. Plugging in to find SR, 8 times 7 is 56. 56 minus 5 is 51. So SR is 51. Moving on to RT. So RT is the whole diagonal of the rhombus. And since it's a rhombus, just like a parallelogram, the diagonals do bisect each other. So RT, we only know 1/2 of it is 5z plus 5, but that variable z is also located in the 2/2 of the other diagonal. I'm going to use the other diagonal to set up an equation to find z since I do know both halves. I'm going to set up the equation 3z is equal to 4z minus 8. And subtracting 4z from both sides, I have -z is equal to -8. Dividing both sides by -1, I have z is equal to 8. Now that I have my z value, I can plug in to find the half of this diagonal. Then I'll know this half, and then I'll get the whole thing. So 5 times 8 is 40, plus 5 is 45. So this half of the diagonal is 45. That makes this half also 45, which makes the whole diagonal RT have a length of 90. And finally, we need to find the measurement of angle TAS, which is this angle right over here. I know that in a rhombus, the diagonals are perpendicular. That means when they meet, they form 90-degree angles. So I know I have a right triangle over here. Now, in a triangle, all three angles always add to 180 degrees. If this one's already 90, 180 minus 90 is 90. So these two angles also have to make 90 when we add them together. I'm going to use that fact to make the following equation. 9y plus 8 plus 5y minus 2 is equal to 180. Combining my like terms, 14y plus 6 is equal to 180. Let me subtract 6 from both sides. I got 174, and then divide by 14. Oops, let me try that one again. 180 minus 6. Oh, my bad. These two angles need to add to 90 together. I said it out loud, and then I wrote 180 instead of 90. My bad. This one's already 90, so the other two angles need to make 90 together to make that full 180. So we have 90 minus 6 is 84. Divide by 14, and I get y is equal to 6. Now that I have my y value, all I need to do is plug in to find the measure of angle TAS. 9 times 6 is 54, plus 8 is 62. So angle TAS is 62 degrees. Moving on to the next question. First, I need the area of triangle Dan. So I'm going to box the triangle. I want all the vertices to be included when I box it. Oops, there we go. Uh-oh. Uh-oh, I want to do this accurately. That was hard to do on the computer. So I've completely boxed in my triangle, making sure to hit all the vertices. And now what I see is that I've made 3 right triangles. I'm going to call them triangle 1, 2, and 3. So first I'm going to find the area of the hole. And the whole box is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So length times width, 12 times 11 is 132. Now we need to find the area of the triangles to subtract them off. So this triangle is 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this one's 11. And let me count up the rest of the bases and the height, so please count them up as well on your own. Okay, so area of a triangle formula is 1/2 base times height. So for triangle number 3, that would be 1/2 11 times 3. For triangle 1, that would be 1/2 9 times 7. And for triangle 2, that would be 1/2 of 12 times 4. So half of 11, half of 11 times 3 is 33 over 2. 9 times 7 is 63, so that would be 63 over 2. And 12 times 4 is 48, so that would be 48 over 2. So now I'm going to go over to my calculator, and I'm going to put the whole minus the surrounding triangles to get the triangle that I actually want. So on my calculator, 132 minus parentheses. Let me get my fraction button. 33 over 2. I want to make sure that I enter this in correctly, else I'll be really annoying. Plus 63 over 2 plus 48 over 2. And it works out nice enough that when I type this into my calculator, I get a whole number. I get 60 for the area of the triangle. Remember, the whole minus the parts gives us what we are looking for. Okay, then it asks for the perimeter of the triangle. To get the perimeter, we just need to use the distance formula for the 3 sides. So I'm going to pause the video and just find the distances. Then I'll unpause it so you can check your work. Okay, when I use the distance formula, I got radical 160, radical 130, and radical 130. So adding those all together, I have 2 radical 130 plus radical 160. You can simplify the radicals if you want to, but the question does not ask for it in simplest form, so leaving it just like this is totally fine. Okay, moving on, we have a proof question. And in the proof question, we're told that quadrilateral PROE is a rhombus. So if I know it's a rhombus, the first thing I know about it is that all of the sides are equal, as well as that it has the properties of parallelograms. So there's nothing about, there's no diagonals drawn in, so none of the properties about diagonals are probably going to be useful to us. So let's see what else we're given. Let's see what the question is, and let's see what else we need to figure out here. So it also tells us that SPR, that's this angle right over here, is congruent to angle VOR. So it seems like the question is missing what you're trying to find. It looks like it got cut off. So I'm just going to write it over here. We need to prove that angle SPE is congruent to angle VOE. So right now we have the whole angle SPR, we want just the piece. We have the whole angle VOR, we want just the piece. So another thing that we do know, oh, my bad. Let's edit. Let me get what the proof statement is. Let me write it down, and then we'll go from there. Sorry. The proof statement, I just looked at the original question, is to prove SE is congruent to EV. So we want to prove that this side of the triangle over here is congruent to this side of the triangle over here. So since these are corresponding sides of the two triangles, this is going to be a CBCTC question. So first, we are going to need to prove that these two triangles themselves are congruent to use CBCTC for these two sides. So the angles that we have are too big. They're not inside the triangles that we want. So we want to get the angles that are actually inside those triangles so we can use it to prove the triangles congruent to each other. We do know that since a rhombus has all the properties of a parallelogram, that the opposite angles are congruent. So I do know angle EOR is congruent to angle EPR once again because opposite angles of a rhombus are congruent. Now I can do the whole minus this piece to be left over with the piece that I want inside the triangles. And that would be the subtraction postulate to take the large angles, subtract off the piece that we don't need, and get information about the piece inside the triangle that we're interested in. When we're making large information smaller, that is the subtraction postulate. And then, as you can see here, we also do have vertical angles, which are always congruent to each other. Once we have all that information, we can see that the two triangles are going to be congruent by angle, side, angle, angle, side, angle. And then finally, we can prove SE congruent to EV using CBCTC. So I'm going to take a second and write that up into proof format. I'm going to pause the video so then you can take a look at the work. Here's the proof written out with everything that we talked about. You can take a second, pause the video, so that way you can match up what's written in the proof to what we marked in the diagram. Okay, here's another proof question. So we're told here that we do have a square. So all the properties of parallelograms, rhombuses, and rectangles apply to this square. And we want to prove that AF is congruent to DE. So here is AF. I can see that AF is a side of this triangle right over here. And DE right here, I can see that that's a side of this triangle here. So now I have my two focus triangles, so I can narrow down a little bit what I need to do. I need to prove these two triangles congruent. And once I do, I can use CBCTC to prove the corresponding sides AF and DE congruent to each other. And that's my goal. I know this is a square, all the properties of parallelograms, rhombuses, and rectangles. So just like a rectangle, the angles are 90-degree angles. And I do know, just like parallelograms, rhombuses, and rectangles, the opposite sides are congruent to each other. Now, the last thing that I need comes from my given information, and I almost missed it, that BE is congruent to FC. BE is not the full side of this purple triangle. BF is. CF is not the full side of this blue triangle. CE is. To make BF, we need to add EF to BE. And to make CF, we also need to add EF to CF. So EF is congruent to itself. That's the reflexive property. So we can do BE plus EF to get this whole side, CF plus EF to get this whole side. And that gives us the last side that we need, side, angle, side, side, angle, side. Once we know the triangles are congruent by side, angle, side, we can say AF is congruent to DE by CBCTC. Here's the proof. Pause the video, compare to what we have marked in the diagram. Everything that was mentioned in the plan is now in the proof. Okay, moving down to the next proof question. So we're told here that RKMP, that's this quadrilateral on the inside, is a parallelogram. So it has all the properties of parallelograms because it is a parallelogram. We also know that angle JRK is congruent to angle PMO, and we know that we want to prove that RJMO is also a parallelogram. So let's start with the parallelogram on the inside. We know in a parallelogram that opposite sides are congruent, and that also gives us a pair of congruent sides in these two triangles here. So I have an angle and I have a side in these two triangles. I also know that opposite sides are parallel in a parallelogram. That's both pairs of opposite sides are parallel. So it would be really helpful if I could get this angle here and this angle here. So I just want to highlight my parallel lines and my transversal. And I see that this is top right. Here's an even easier way. Since this is a parallelogram, opposite angles in a parallelogram are congruent to each other. And we know that these two angles are supplementary, and so are these two angles. Since these angles are both supplementary to congruent angles, that means that these angles have to be congruent to each other as well. Supplements of congruent angles are congruent. So now we have that these two triangles are congruent by angle, side, angle. And then using CPCTC, we can say that the corresponding sides are congruent. And we can also use CPCTC to say that the corresponding angles are congruent. So that gives us a pair of congruent opposite angles. And since we knew that this was already a parallelogram, not only are these angles that are opposite from each other congruent, but so are these angles. So using the addition postulate, we can combine the pieces and get this whole angle congruent to this whole angle. And then what we have is both pairs of opposite angles congruent to each other. So I actually did not end up using this, so I'm going to get rid of it from the plan. We can prove that the opposite angles are congruent, making quadrilateral RJMO a parallelogram. So I'm going to just write up this proof so you can see exactly what that looks like. This proof is a bit complicated, so please take a minute and pause and compare what's in the proof to what we marked in the diagram. Ultimately, I ended up proving that it's a parallelogram by proving that both pairs of opposite angles are congruent. I think that is the easiest method here. In order to do that, I had to first prove these two triangles congruent to each other. CPCTC got me angle J congruent to angle O. And once I had these pieces, I could add them together to make the whole angle R and the whole angle M to show that both pairs of opposite angles were in fact congruent, making RJMO a parallelogram. Next proof, there were a lot of proofs on this review sheet. The more practice, the better. So here we have that FGHJ is a parallelogram. So that's this big parallelogram, this big quadrilateral on the outside. And we're also given that FK is congruent to HL. Keep in mind that FK is a piece of one of the diagonals, and so is HL. It's a piece of one of the diagonals. We want to prove that KGLJ is a parallelogram, so that this inside quadrilateral is also a parallelogram. So remember, in a parallelogram, the diagonals bisect each other. So if the large quadrilateral is a parallelogram and one of its diagonals is JG, and that's bisecting, it's being cut equally into two congruent parts. Now, notice how JG is also a diagonal in this small quadrilateral. So I already know that one of its diagonals are split in half. Now, if I can show that the other diagonal is split in half, I would be good to go. Then I would have a parallelogram, because if diagonals bisect each other, we know the quadrilateral is a parallelogram. The other diagonal of the big parallelogram that we already know is a parallelogram is FH. So I know that FO is congruent to OH. Now, since I have the whole and the part, and I want this piece, I can use subtraction to do whole minus this piece to give me this, whole minus this piece to give me this. And once I have KO congruent to OL, I know that JKGL is a parallelogram because the diagonals bisect each other. I'm going to write this up as proof. Here is the proof for this one. You can take a minute and pause the video and compare to what we marked in the diagram. Okay, next proof, BE bisects angle DBG, so that means it's being split into two equal parts. We know that angle DBE is congruent to angle DEB, and I know that BD is parallel to GE. We need to prove that DBGE is a rhombus. So a rhombus first needs to be a parallelogram. So I know that one pair of opposite sides is already parallel. And if you take a look, I do have congruent alternate interior angles. So I can conclude that the other pair of opposite sides is also congruent to each other. And remember, a special property of a rhombus that makes it different from a regular parallelogram is a rhombus is a parallelogram whose diagonals bisect the angle. And since we know that these sides are parallel, we do know that the alternate interior angles are congruent. So as you can see here, this parallelogram is also a rhombus because the diagonal bisects the angles. So I'm just going to take a second and write this up into a proof. You can pause the video and then when the proof is written up, to look it over and compare with what you have. Okay, here's the proof. You can take a minute and pause the video and compare to what we have in the diagram. Okay, last proof. So we have triangle ABC where angle ABC is a right angle. So ABC where angle ABC is a right angle. And BE is drawn to AC. So here's BE. Extend, oh, and it says BE is a median. So if it's a median, E is the midpoint, it splits AC into two equal parts. Extend BE through E to D so that BE is congruent to ED. Draw AD and DC. Prove ABCD is a rectangle. Before it can be a rectangle, it first needs to be a parallelogram. Well, the diagonals bisect each other, so it's a parallelogram. One and done. Now we need to prove it's a rectangle. Well, look, it's got a right angle. A parallelogram with a rectangle is a right angle. And that's it. I'm going to pause the video and write up the proof. You can see it. And here's the proof. You can pause the video and compare this proof to what's marked in the diagram. I didn't write out all the givens for this one because it was a lot, but most of the information came from the givens. The fact that BE was congruent to ED came from the givens. The fact that BE was a median to side AC of the triangle came from the givens. and the fact that angle ABC was a right angle did come from the given.